Hello student, myself Nimesh Prabhakar. Welcome to Process Control lecture series. In my previous lecture, I discussed about the position and velocity algorithm in terms of the controller, and then we discussed about the bumpless transform. Now, in this lecture, we first discuss about the integral windup, then we discuss about the controller bias. So here we discuss two topics. Now we start the first one topic, integral windup. So now, first one question come in our mind, what is windup? So now we understand. When the controller reach the actuator limit, then the actuator becomes saturated and the system effectively operates in an open loop. We know what is actuator. That means we know the controller gives signal to the actuator. Actuator, that means we can say this is a valve that used to open or close the system, or we can say any device that used to provide the output to the system. So here when the controller reaches the actuator limit, then the actuator becomes saturated and the system effectively operates in an open loop. That means there is no controlling action at that time. The integral term and the controller output may become really large, that means large overshoot. The control signal remains saturated even if the error began to increase, hence very bad transition. For example, now we understand when a car is on steep hill, the throttle saturates when a cruise control attempts to maintain a speed. Now we understand what is integral windup. So here we take the example of the PI controller, that means proportional plus integral algorithm we have taken. So this is the general equation of the PI controller. CO plus CO bias plus KC ET plus KI integration ET dt. So here this CO indicates the controller output signal, CO bias indicates the controller bias or null value. What is bias? Why we require bias signal? We will discuss after completion of this topic, that means integral windup. Then we discuss about the bias. ET, here ET indicates the current controller error. That means error is nothing but the difference between the set point and process variable. SP indicates the set point. PV indicates the measure variable or the process variable. KC indicates the proportional gain, or we can say as a tuning parameter, and KI is known as the integral gain and is also known as the tuning parameter. So this is the general equation of the PI algorithm. Now we understand here the effect of integral windup. The integral sum start accumulating when the controller is first put in automatic and continues to change as long as controller error exists. If the error is large enough and persists long enough, it is mathematically possible for the integral term to grow very large, either positive or negative. You can see this is the action in the figure. So here this equation is become, that means this integral term is become very large. So this large integral, when combined with the other term, that means in the proportional term, now we add the integral term. in the equation can provide the CO, that means controller output value, that cause the final control element to saturate. That is, the CO derives the FCE, that means final control element, we can say as the pump, valve, compressor, anything final control element, to its physical limit, or fully open, or maximum, or fully closed, or maximum open, we can say. And if this extreme valve is still not sufficient to eliminate the error, the simple mathematics of controller algorithm, if not jacketed with the protective logic, permits the integral term to continuous growing. Now we understand how. If the integral term grow unchecked, the equation above can command the valve, pump or compressor to move 110%, 120%, and so on more. Clearly, how we can the FCE, that is final element control, reach to its full 100% value, then last command have no physical meaning. That means 110, 120. Consequently, no impact on the process. That means is known as the saturation effect. It not affect on the controlling system. Now we understand this integral wind-up system by using this graph. To better visualize the problem of wind-up and the benefit of the anti-wind-up protection, consider the plot from the heat exchanger process that is shown in the figure. To the left is the performance of PI controller with no wind-up protection. So you can see here in the left hand side of this graph, this is a no wind-up protection. Same as in the right hand side, the performance of the same controller is protected by anti-wind-up system. So you can see this is the difference between the anti-wind-up control system and the wind-up control system, without wind-up control system. For the board controller, the set point is tapped from the 200 degrees centigrade up to 250 degrees centigrade and back again. As shown in the lower track on the plot, the controller moves the controller output to 0%, closing the value completely at. This is not sufficient to move the PV up to a new set point. To the left in the plot, the impact of wind-up is degraded controller performance. When the set point is tapped back to its original value of 200 degrees centigrade, the wind-up condition causes a delay and the controller output action. In this term, cause a delay in the PV response. To the right in the plot, anti-wind-up protection permit the CO as touch PV the response permanently to command to the return to the original SP value of the 200 centigrade. Now we discuss about the anti-wind-up system. That means how we can avoid the wind-up. So first one system we discuss about anti-wind-up system. You can see this is the diagram for that. There are many ways to avoid the wind-up. One method is illustrated in this figure. The system has extra feedback part. You can see this is the extra feedback part in this system. That is generated by the measuring the actual actuator output or the output of the mathematical model of the saturating actuator and forming an error signal ES as the difference between the output of the controller V and the actuator output U. Now the signal ES is fed to the input of the integrator through the gain K. You can see this is the feed. The ES is 0 when there is no saturation, and extra feedback loop has no effect on the system. When the actuator saturates, the signal ES is feedback to the integrator in such a way that the ES goes towards 0. This implies that controller output is kept close to the saturation limit. The controller output will then change as soon as the controller change sign and integral windup is avoided. The rate at which the controller output is reset is governed by the feedback gain, that means KT. A large value of KT gives a short reset time. The parameter KT can, however, not be too large because measurement error can then cause an undesired reset. A responsible compromise is to choose KT is equals to 1 upon Ti for the PI controller, or for the PID controller we can choose KT is equals to 1 upon under root Ti. So this is the first one, anti-windup system. Now we discuss about the second one type of system to use for the controlling the windup system. So here, back calculation use feedback of the difference between the desired, that is desired value, this is V, and the actuator control U as an input for the integral term. If V is not saturated, then set U is equals to V. If V is at the saturation value, then the set U is equals to saturation value, or we can say the process is in open. The error signal ES is equals to U minus V. It is non-zero only when the actuator is saturated, or we can say no effect on normal operation. The normal feedback path around the process is broken and a new feedback path around the integrator is formed. The integrator input becomes ES upon KT plus E into K upon KR. So this way we can reduce the effect of the windup, or we can say this is the anti-windup strategy. Now we discuss about the second one topic. This is the controller bias. So now to understand the controller bias, here we take the example of the proportional controller. So the P only controller compute a controller output action every loop sample time T as CO is equals to CO bias plus KC into ET. And here we know CO is indicate the controller output, CO bias indicate the controller bias or null value, KC indicate the controller gain, or we can say the tuning parameter, and ET indicate the controller error. We know the error is nothing but the difference between the set point and the process value. So this is the general equation for the proportional controller. Now by taking this example we understand the controller bias, and this SP is indicate the set point and PV indicate the process value. Now let's suppose the P only controller algorithm so above is used for the speed control in an automobile. That means we use this controller to control the speed of the car. And the CO, that means controller output, is throttle signal adjusting the flow of the fuel to the engine. That means here we control the fuel signal, that means fuel flow we control by using this controller. So let's let us suppose that the speed, that means set point is 70 km per hour and the measure value is also 70. That means there is no error. So at that time we what? Error signal is 0 because PV is equals to SP. So ET is become 0. So from the equation we can write the CO is equals to CO bias and Kc and ET is equals to 0. So last term becomes 0. So CO is equals to become CO bias. Now here we understand the importance of CO bias. Why we require bias signal here. So if CO bias is also 0, so what happened in this case? So CO bias is 0, then we set point equals measurement. The above equation say that the total signal controller output is also 0. That means no signal is go in the throttle side. This make no sense. That means clear, if the car is traveling 70 km per hour, then some baseline flow of fuel is going to the engine is necessary. Otherwise car is stopped. So here we require a bias signal for the minimum operation of the car to maintain the speed at 70 km. This baseline value of CO is called the bias or the null value. In this example, CO bias is the flow of the fuel that the manual mode causes the car to travel the set speed of 70 km per hour. A P-only controller bias, sometimes called null value, is assigned a value as a part of the controller design and remain fixed once the controller is put in a automatic mode. So this is the importance of the controller bias in the P-only controller. So that's why we give the bias signal in the controlling things. So in this lecture we discuss about the integral windup and then we discuss about the controller bias. So we discuss mainly two topics. First one is the integral windup and controller bias. Thank you.